Hi, my name is Jean Ederscu, and this is my mini lesson on the potential of hydrogen, or pH. These are just some of the topics that students should be familiar with prior to this lesson. So, atomic properties like electronegativity, types of chemical bonds, polarity, um, balancing equations, reaction equilibrium, and so forth. So, the aim of this mini lesson is to understand the extent of a molecule's potential to deprotonate in aqueous solution and then quantify the number of protons in solution at a given time. These are the key words, and the takeaway skills is to quantify acidity or the amount of protons in solution in terms of molarity and pH. So, as I said, pH is the quantification of hydrogen cations in aqueous solution. The hydrogen ions are quantified in terms of moles per liter, which can be converted to a value on the pH scale. pH scale is a log-based scale that ranges from 0 to 14. Concentrations of hydrogen ions or pHs can exist outside this scale, but for most laboratory applications, you will find that solutions will fall within this range. Not every molecule that has hydrogen atoms in it will produce hydrogen ions in aqueous solution. Those that do are those that contain a polar covalent bond between hydrogen and a more electronegative atom. In this example, I use HCl, where hydrogen is bound to chlorine. The difference in electronegativity between hydrogen and chlorine creates a dipole, and therefore there is a potential for hydrogen to deprotonate in the presence of a polar solvent. Water is a polar solvent that itself has partial charges, which then stabilize the charges of the ions in solution. Hydrogens that can readily dissociate in water are considered acidic. Now, molecules like HCl can produce more hydrogen ions in aqueous solution than other types of molecules that also contain a polar covalent bond. So in this example, I show you acetic acid. Acetic acid contains a polar covalent bond between oxygen and hydrogen. Similarly to HCl, partial charges accumulate on each of the atoms. However, in this case, the electron distribution throughout the rest of the molecule of acetic acid stabilizes this bond. Therefore, the propensity of this bond to dissociate is lower than that of HCl. So HCl, having a high propensity to deprotonate, is a strong acid, and acetic acid, having a lower propensity to deprotonate in aqueous solution, is a weak acid. The number of free hydrogen ions in aqueous solution corresponds to a pH value. So when there are a large number of hydrogen ions in aqueous solution, we have a low pH number, and this is acidic. Whereas when we have very few hydrogen ions in aqueous solution, we have a larger pH value, and this is more basic. So the relationship between the pH value is the negative log of the hydrogen ion concentration in terms of moles per liter. So in this example, we are given that we have 1 times 10 to the negative 12 moles per liter H plus ions. What is the pH? All we do is plug into this formula, and we determine that the pH equals 12. Now, you won't always be given round numbers, but a good way to estimate what the pH is to look at this exponent. Now, in that example, you were directly given the concentration of H plus ions to plug into the formula to determine the pH. Now, what if instead you were given the concentration of the acid? Is that exactly equal to the number of H plus ions in solution? Not necessarily so. So the first step is to determine if the acid that you are referring to is a strong or weak acid. There's essentially 6 strong acids. Everything else can be considered a weak acid. Strong acids completely deprotonate in water. In this reaction equation, we have the acid represented as H for the proton on A for the acid. When it's dissolved in water, you'll produce H plus ions, which is also referred to as H3O plus, and the deprotonated acid. Strong acids will convert to 100% of these products. Therefore, if you're given the acid concentration, you can say it's equal to the proton concentration. In this question, we're asked to determine the pH of a 5 millimolar solution of HCl. HCl, or hydrochloric acid, as we know, is a strong acid. Therefore, the concentration of HCl equals the concentration of H+, and we can plug that directly into our pH formula. The negative log of 5 times 10 to the negative third equals 2.3. Now, weak acids do not easily deprotonate in water, meaning they're going to produce fewer than 100% of products. So in this case, you will have a mixture of the protons, the deprotonated acid, and the protonated acid species. Therefore, when you calculate the pH of a weak acid in solution, you have to consider its equilibrium constant, as it's moving back and forth between both protonated and deprotonated states. Here's a simplified version of this reaction scheme. Now, like any equilibrium, the KEQ is equal to the concentration of the products over the concentration of reactants. So here, this KEQ is referred to as Ka, or the KEQ of acid. So we multiply the concentration of H plus ions to deprotonated acid concentration and divide that by the concentration of protonated acid. There's going to be times when you dissolve a weak acid in solution that there's more protonated acid than deprotonated acid. However, when the concentration is equal, or a 50-50 mixture of deprotonated and protonated species, the pH of the solution equals the pKa. And the pKa is just the negative log of the Ka. So given all of this information, we can solve for the H plus ion concentration of a weak acid in solution and then calculate pH. So in this next problem, we're solving for the pH of a 5 millimolar solution of acetic acid. Because acetic acid is a weak acid, we need to be given some information about its equilibrium constant. Here we're given that the pKa equals 4.76. So we know the formula for Ka, and we also know that when an acid dissociates, it's going to create equal parts deprotonated acid and H plus ions. We also know the relationship between pKa and Ka. Therefore, 10 to the negative pKa, or 10 to the negative 4.76 molar, is our Ka. So plugging this in, 10 to the negative 4.76 molar equals x squared over the concentration of acid, which is 5 times 10 to the negative 3 molar. Solving for x, we determine that the hydrogen ion concentration is 2.95 times 10 to the negative 4 molar. Now that we've solved for H+, we can go ahead and plug this into our pH formula and determine that the pH of a 5 millimolar solution of acetic acid is 3.53. Notice the difference in pH of a 5 millimolar acetic acid solution and that of a 5 millimolar HCl solution. A 5 millimolar HCl solution has a pH of 2.3, where a 5 millimolar acetic acid solution has a pH of 3.53. This indicates that acetic acid produces fewer protons in solution. In this next problem, we're asked to solve for the concentration of H plus ions in a solution of nitrous acid at a pH of 5 and with a pKa of 3.15. Now we're given the pH, so we can directly solve for the H plus concentration using the pH formula here. Using your log rules, you then solve that the concentration of H plus ions equals 10 to the negative 5 molar. In the next part of the problem, we're asked to solve for the concentration of nitrous acid itself in aqueous solution. Again, we're given that the pH is 5 and the pKa is 3.15. Now remember, nitrous acid is a weak acid, so this pKa value is relevant. If you were instead talking about nitric acid, you would solve this problem a little differently. So the other information we know is the Ka formula. We also know the concentration of H plus ions. And H plus ions is going to equal the same concentration as the deprotonated acid. So all we need to solve for now is the HA concentration. We find that the concentration of HA is 1.41 times 10 to the negative 7th molar. So far, we've learned how to calculate the concentration of H plus ions in a given acid solution. We've also been able to correlate this concentration to a pH value and how we implicate pKa in these calculations. So the next topics to study are polyprotonated acids, further understanding pKa charts, base chemistry, and those related concepts. Thank you, and that is all for this mini lesson.